Welcome back. Hopefully you've had a chance to look at the first video where I discussed voltage and defined it, and we talked about some different scenarios of what it means. This is the video where I'm going to talk about some real life situations such as batteries. We'll understand how that works a little bit. We'll think about wall outlets and how those are different, and bring up this whole idea of AC versus DC power. I'm not going to spend a lot of time on electrochemical cells because to do those justice, they can be fairly complicated, but I'm just going to give you an incredibly brief overview of how something like that works, just to kind of fill in the picture a little bit, because this type of thing, this chemical process, is really the driving force behind a battery. Alright, so to start with this idea of DC power, DC stands for direct current, which means that we are always going to have a constant voltage in an ideal situation. If I take an electron from the negative terminal down here and I move it to the top terminal in order to do something like light up a light bulb, I will immediately replace it down here with another electron, and I will figure out a way to get rid of that electron that I just sent up there so that I can always maintain the same electric potential. That's the main idea behind a battery. I mentioned this before, but it's truly a chemical process that's going on inside of a battery. The first video that I showed you gave us a very straightforward way to think about this change in voltage, where I'd have an excess of charge, and it gets a little bit more complicated when you start to bring all the different chemicals and metals into this. So a common battery that you might run across has a voltage of 1.5, for example. There's a couple different ways that I can configure batteries. You'll notice that often you have more than one battery in a particular thing, like in your camera or in a remote control car or something like that. If you configure them so that the batteries are side by side and that these two positive terminals are connected by a wire, remember we said any time that I have conductors touching one another, they have to be at the same electric potential. So when I do this, I still am only going to have 1.5 volts between the negative terminals and the positive terminals. What I've done is I've basically increased the amount of charge that I have the ability to store within the batteries that I can transfer from one terminal to the other. So I've increased the lifetime of this battery pack by a factor of 2 if I have 2 batteries. In other situations, you'll see batteries stacked one right on top of the other. If you think about why this works, again, remember that anytime 2 conductors are touching one another, they will immediately go to the same electric potential. So in this middle location, the negative terminal of the top battery is now at the same electric potential as the positive terminal of the lower battery, which means that I've now increased the voltage across this negative terminal all the way up to this positive terminal by a factor of 2 because there are 2 batteries. So in this case my voltage added and I was able to get 3 volts out of this system. The advantage here is that I might be able to drive a motor that needs 3 volts. Maybe it wouldn't work on 1.5 volts. We're going to move on from here and take a look at a FET simulation because everybody knows how much I love my FET simulations. If you're not familiar with FET, it's from the University of Colorado, and they are some free simulations that people can use to help understand different science topics, and so they're pretty good. The one that I'm going to use in this particular lesson is called Circuit Construction Kit. And it's going to allow us to take a peek at a DC circuit as well as an AC circuit actually. This is the circuit construction simulation from FET. In advance I've constructed some circuits here. This top one is an AC circuit, which we haven't quite started talking about yet. We want to focus down here for a moment on the DC circuit. I've had the opportunity to go ahead and construct the circuit. I've put in a battery here. So this is a DC power supply. There's going to be a constant voltage from this positive terminal down to the negative terminal. I've put a light bulb in my circuit here. This is going to be our way of kind of quote unquote controlling the electron flow. We are going to slowly allow electrons to flow through the battery, not really through the battery, but from the negative terminal to the positive terminal. And we're going to ask those electrons to do a task for us in the process. In this particular case, the task is simply run through a wire that has a lot of resistance. It causes the filament of the light bulb to heat up, and then it shines light for us, and we like that. Now, nothing's happening right now because I also put in a switch. So right now my circuit is closed. I still have a voltage across my battery. By definition, I have to have that as long as it's a good battery. I'm just not allowing any possible pathway for the electrons to get from the negative terminal to the positive terminal. So things just sit there static and the light bulb is off. As soon as I close my circuit though, I'm allowing for the electrons to flow. And you can see it lights up nice and brightly. So we have electrons going from the negative terminal all the way through this. It's going to go through the light bulb, and then they're going to go into the positive terminal. Okay, we are going to transition from that DC circuit up to this AC circuit. AC stands for alternating current. It has a very different feel to it, even though it's going to get essentially the same result for us. I'm going to go ahead and close the AC circuit so that we can just see what happens. I think that's the best thing to do here. You can see I still get some light out of my light bulb. I have my AC power supply, but what you hopefully are observing is that an electron, any given electron, is just wiggling back and forth, back and forth. We would say that this is in a sinusoidal pattern, so like a wave type idea, just back and forth, back and forth. In the United States, this back and forth happens 60 times a second, so we say that our outlets are at 60 hertz. We can still steal energy from these electrons as they go back and forth. Inside of here, they're still causing friction on this filament and still causing this filament to heat up. You can see that in an AC circuit, it shows that the light bulb is not actually on all of the time. In practice, this little filament can stay hot enough to potentially still shine light, even for that brief moment in time when you stop the electrons moving back and forth. So it's possible for the light bulb to still be totally shining even though you're just bringing the electrons back and forth, back and forth. But to cause them to go back and forth, you still need a voltage. So an alternating current, an AC circuit, must have a changing voltage. So here we are on AC power, the thing that's in our wall socket. We have this idea that I already brought up where the voltage is back and forth, back and forth, back and forth. So as a function of time, this is what the voltage might look like. It might be at a particular peak for a moment, and then sometime later it's actually at 0 volts. Between two different wires here, two different spots, and we're going to talk about that in a little bit more detail. But remember, a voltage is just perhaps a buildup of charge on one of the wires back behind the outlet compared to the other. So we have a buildup of charge, and then it's going to go and it actually spends a moment where they have the same effective charge for just a brief moment and no voltage between them, and then it's going to overshoot and go in the other direction, where if it had too many electrons on the live wire up here, now it's got too few, and it'll just do that back and forth, back and forth, back and forth. Again, in the United States, we have 110 volt wall sockets. In practice, that might mean that we're about 115 volts up here and negative 115 volts down there. As I mentioned before, we're looking at about 60 hertz in the United States. I think it's something like 50 hertz in the UK, though probably shouldn't quote me on that. Let's look at the guts of this wall socket now. There are 3 different things usually with any particular wall socket. The first is what we call the live wire. That's the thing that carries this excess charge. That's the one that's doing all the action. So that voltage graph that I showed you before where it goes from high voltage to low voltage, that happens on the live wire, and it's going to constantly oscillate. So the power company off somewhere is in charge of maintaining that, keeping it going up and down, up and down, up and down. The next wire is the neutral wire, and by the way, I'm putting the typical colors here in the United States, where the live wire is black, the neutral wire is white, and we'll get to the next one in just a moment. But the neutral wire is just a piece of metal, and it's not particularly charged in one way or the other. And in fact, the job of the electric company in this case is to try to keep that neutral so that I can maintain a nice voltage between the charged wire and the neutral wire. The third wire is the ground, which is typically green, or at least often green, and it literally goes to the ground in some way, shape, or form. Sometimes it might go to a copper water pipe in your house, but in some way it's going to attach itself to the ground. And that is there as a safety precaution. So if you had a situation where you had a large amount of charge, we would say that is a large current, trying to transfer from the live wire, this ground wire in many cases can safely take that charge away and just distribute it inside of the earth, which is much better than having it go through, say, your computer, blowing up your computer, or even worse, going through you and causing a great deal of harm to your body. So let's take a look at this voltaic cell. This is the thing I said I'm not going to go into great detail. It requires some chemistry to understand this. You have two solutions, and inside of these solutions they have ions, usually different inorganic ions. And we have two different metals sticking in the two different beakers. Now, different metals have different affinities for electrons. So one metal may want and need electrons more than another metal. When you pair up two different metals in a situation like this, one of them becomes the negative terminal effectively, and it is an electron donor. It will allow its electrons to go to the other metal, kind of for the greater good. And in the process, we can say that there's a voltage built up between these two different metals. So if one metal is an electron donor, then the other metal is an electron acceptor. And so you can think of this as being the negative terminal of a battery, and this is the positive terminal of a battery. Because I have these two different electrodes, or we can call them these two different terminals, and they have a different desire for electrons, we can say that there is actually a voltage. And so you don't get huge voltages out of these things. You may get a fraction of a volt, for example, 0.6 volts. So we don't get large voltages, but we can get volts just by sticking these different metals into solution if done correctly. There's also this other middle thing that kind of has to be there. This is called a salt bridge. Its job is to carry some of the ions that are in solution from this side to the other side, and carry some that are on this side back over here. If you like, think of it as completing a circuit. So if I didn't have the salt bridge, all I would have is one metal sitting here and a different metal sitting here with an open circuit, no actual path for electrons to travel through. So the salt bridge you can really think of as just a required thing that allows charges to transfer from one side to the other. Now for this type of thing though, those charges are on different ions, and so the full ion actually travels from one solution to the other. Big picture idea, voltage we said was a difference in the electric potential from one location to another location. It is a change in potential energy per amount of charge. We talked about DC power and how it maintains a constant voltage across the terminals, and we compared that to AC voltage and how it actually has this changing voltage that goes up and down, and it causes the electrons to go back and forth inside of a wire. I also briefly talked about this electrochemical cell. Again, I think that's somewhat important to understand from the standpoint of knowing that it's this type of idea that allows us to get these batteries down here. So That's all I have for you in this particular lesson. If you think you got it all, let your computer know.